Hello and welcome. In the previous video, we saw the capacitor. In this video, we're going to look at a new component called the coil. A coil is a winding of conductive wire. As we can see in this photo here, with this winding possibly being around a ferromagnetic material. So here is the symbol for the coil. And one of the characteristic properties of the coil is its opposition to the variation of current in its turns. So when there is a coil in an electrical circuit, it will prevent the current from varying too quickly. We can differentiate between an ideal coil, which is the purely theoretical case, and a real coil, the practical case. So we'll start with the ideal coil, whose representation is here. This coil is crossed by a current I and has a voltage U across its terminals. Well, the Ohm's law for this ideal coil is U equals L di dt. So U, the voltage across the coil, is equal to L. L is the inductance of the coil multiplied by the derivative of the current flowing through this coil. So the inductance of the coil is a bit like the capacitance of a capacitor or the value of a resistor. It's what is specific to the coil. It's its value. Inductance, its unit is the Henry, whose symbol is an H. Then there is the real coil, which is represented here. And in fact, the real coil is a coil with a resistor in series. So in practice, coils always have a small internal resistance. And at that point, Ohm's law is U equals R plus L di dt, as we can see here. So here, it is very important to differentiate between these two cases and to remember the Ohm's law of a coil. We're going to do a small energy study of the coil, taking the ideal case, which we see here. So with Ohm's law, U L di dt, if we have a coil and we apply voltage to this coil, a current will be established. So the current will go from 0 to a certain positive value, and therefore the derivative of the current will be greater than 0. The voltage will be greater than 0 and the power will be greater than 0. So the coil will store energy in this case. Next, if we open the circuit, meaning that we go from this current I to a current of 0. In this case, the derivative of the current is negative. According to Ohm's law, the voltage will be negative and therefore the power will be negative. This means that the inductor will return the energy it had stored. And so the formula for the energy stored by the inductor is as follows. W is equal to 1/2 of Li squared. We will now see how the current is established in a circuit with an inductor. For this, we will take the following example, which is a circuit with an inductor and a resistor in series, this circuit being supplied by a voltage U. So initially, this voltage U is equal to 0, and we will change this voltage U from 0 to capital U. So when this transition occurs, the inductor cannot store energy instantaneously, and so the current will always be 0. Here. Given that we have UR, which is equal to RI, UR is equal to 0. And since we have the mesh law, U is equal to UR plus UL, we see that the voltage UL is then equal to U. And that's exactly why when we apply a voltage, which we call capital U, the voltage across the inductor then becomes equal to capital U. Then, little by little, the inductor will store energy and the current will then increase. This causes the voltage UR to increase as well, and always to respect the mesh law, the voltage UL will decrease. So that's the transient state of the inductor. And once UL has finally reached 0, the inductor has stored all the energy it could within its magnetic field. UR reaches a certain constant, and the current is then established. In steady state, the inductor behaves like a closed switch, like a wire. Here we have the equation that governs the establishment of the current in the circuit. So it's IT plus L over R d over dt is equal to E over R. We see that it's a first-order differential equation whose time constant, tau, which is equal to L over R. We will now see how the current drops to zero in a circuit with an inductor. And we'll go back to the previous case. With the coil that stored the energy, and we reduce the voltage of U to zero. In that case, the coil cannot restore energy instantly. Therefore, we always have I which has a certain value, U on R, so U of R is always at the value U. And there, according to Kirchhoff's voltage law, in this case, UR plus UL is equal to 0. So that means that UL is equal to minus U. Then, little by little, the coil will release the energy that she had stored up. Therefore, the current will decrease, the voltage UR will decrease, and the voltage UL will also tend towards 0. And this will continue until the established regime, the permanent regime, is in place. The voltages are equal to 0, and the current is equal to 0, and we return to our initial state. This time, the equation governing this phenomenon is I plus L on R, d sur dt, equal to 0. So it's still a first-order differential equation. With the same constant tau, it is always equal to L over R. So what we observe both for the establishment of current and for the cancellation of current in a coil is that it does not happen instantaneously. We can see that it takes some time for the current to reach its steady state. And that's what we saw at the very beginning of the presentation. That's it. The property of the coil is that it prevents the current from varying. The current will vary with a certain transient over a certain time. One small point, if we have a purely inductive circuit like this one, meaning there's no resistance, and we open this circuit, well, on the one hand, we have a coil which stores energy and cannot release it instantaneously. And on the other hand, we cut the circuit, we open this circuit, and that's instantaneous. Well, what's going to happen is there's going to be an overvoltage and there's a risk of an electrical arc. A small spark will appear. So this is a very abrupt opening and we absolutely must avoid it. In conclusion, we have seen a new component, who is the real. And its property is that it opposes the variation of the current in its turns. It energized the coil to store energy, while upon opening the circuit, it will release this energy. Thank you for listening and see you soon.